So we are going to get into your rigid body, work and energy. So you can understand we're dealing with the very first one is a particle, particle systems or particles, and this part is your rigid body. Two different conditions, particle and then the rigid body. And we're dealing with the same stuff, your work, your force, energy, work, energy, and then your impulse and momentum stuff, um, just the different system, the particle system and the rigid body system. That's about it. So make sure you understand that difference. All right. Once again, don't worry about it if we cover it in details, right? That's just for you to listen one time in the lecture. And of course, we're not going to cover the calculus-based calculation for you at all. If you just listen the concept, that's okay. Concept, we can take it out because that is called dynamics, This is just our objective, We will get into work and energy. And we will study the rigid body system. This is after reading your textbook. You don't have to get it, It's just kind of like a review for your reading quiz. I'll do this for you. So kinetic energy, the energy that body needs to move, all right? And that's here in this case due to rotation, because your body, see, moving. Rotation is a form of movement. So your body is moving, so there is kinetic energy to do this motion. And since we're dealing with the kinetic energy, you have 1 by 2, right? So we know that every time we think about the kinetic energy for particle system is 1 by 2 m and then v squared, So right now we're going to move it to the rotation. So it's going to be this, 1 by 2 ig, and then your little omega thing, and then the whole square. Because that's just a rotation symbol, This is a mass, a moment of inertia, and then your omega, the whole square, Of course, these are little, this is just your G point, yes? We do this again and again. I already explained that to you so many times. Alright, then the second one is when calculating the work done by forces, the work of an internal force, right? It doesn't have to be considered. So this is just telling you, like, when you think about the work done by force, usually work and force are related. And I have shown you several times, in past chapters how they're related. Your force is MA, yes. Your work done is also related to the force times your change in displacement, alright, the angle if we consider, your sine and cosine. So you multiply them, and you will get the work done by the force. So when you calculate the work done by the force, the work of your internal force, this time not just an external force. So in this question, we're dealing with the internal force. So at that time, that work, right, of an internal force doesn't have to be considered. That's because they cancel out, So that's because the forces, they act in equal but then in opposite collinear pairs, meaning like they cancel out. So therefore, you don't really have to consider them, That's about it. But you see this when we go into the example problems, And here we get into the application. Oh, okay, the work of the torque. Your torque is again your moment, So that's the torque is developed by this driving gears. See this? So on the two motors, of course, you have two motors right there. On the concrete, this thing, this big giant thing is your concrete mixer. It's transformed into the rotational kinetic energy of the mixing drum. Then we gotta think about work and energy. This chapter, we're dealing with a rigid body like that. So if you know the motor gear characteristics, then how are you going to find the rotational velocity of that mixing drum? Yeah. So these are just a hint for when we apply the work and energy in this chapter. Yeah. So we will see one by one. And here another work done by this soil compactor's energy. Yeah. And it's going to transform into your translational kinetic energy of the frame in the translation and your rotation kinetic energy of the roller and wheels. Yeah, here is your roller and here is the wheel. So we're looking at your translation and also the rotation kinetic energy. It's just basically telling, oh, okay, if we want to get the work done by this, right? Compactors engine, because engine, that's where you create the motion, because you're using the energy from that engine to do this motion. Yeah, so as soon as you get a motion, which is your force going that displacement, you got the work anyway. So the force come out from the energy of that engine and then pushing itself. Yeah. So every time it goes from one location to another, you got your work done. So that's what we're talking about. And of course, we are dealing with the translation and rotation of this roller and your wheel, because this is how we're taking the displacement, all right, for this work to happen. So these are the things that you gotta be able to see it, yeah, when you think about application, yeah, of what we learn theoretically in outside world. So here's something that you think, oh, are the kinetic energies of the frame, yeah, and the roller related to each other? If so, then how? Yeah. So we'll see as we get into the working energy. All right, kinetic energy. Yeah. We're gonna write it. This is our rigid body. That's what we're dealing with. So here we have translation going on, and this is what I'm talking about. The little point. Yeah. Your G point. So if we think about the kinetic energy in a rigid body, we're going to do the summation method, because you're dealing with the translation and rotation, yeah, two of them. So therefore, the very first one, translation, we go with our regular one, m, and then b, yeah, half mv squared. So g is just showing you at what point, yeah, at which point your reference point is going to be in that body. And then your rotation part is your 1 by 2. Yeah, we already did the reading quiz. Of course, your G point, your mass, yeah, inertia, moment of inertia. And then your rotational angular, yes, velocity instead of the regular velocity right there. This is supposed to be omega. And so that's how we calculate the kinetic energy. I love to write it like KE, yeah, K, big K, and then dot a big E for kinetic energy. Because this can be like have confusion with your other, yeah, symbols. So I don't really support, but then we have to stick to this reference textbook. So whatever I want to say is, you can write whatever you want to write as a symbol, as long as you know what you're doing. And of course, you will communicate with teacher or professor or anybody, yeah, that, oh, hey, KE, if I write it as KE, I meant that's the kinetic energy for this rigid body, yeah, things like that. So anyway, so here, given your T is your kinetic energy, so some student get wrong with the talk, but this isn't force, yeah, this is your kinetic energy. And some people get it wrong with the translation force or something like that, test one. But it's okay, I give you anyway. So, but later you will get it, yeah? So anyway, 1 by 2 mv squared for translation part, 1 by 2 I, yeah? And then the omega squared for your rotation part. So that's your kinetic energy. For pure translation, dealing with a rigid body, yeah? So you're dealing with yes, a curvilinear or rectilinear translation. We have two types, yeah. And at that time, your rotation is going to be completely zero, yeah, zero rotation, kinetic energy. So we call that the pure translation, yeah, kinetic energy, which is your T 1 by 2 m, and then V, of course, the G reference point, the whole square, yeah. Then we'll get into pure rotation. At that time, your translation energy is 0. So when pure rotation, oh yeah, I forgot it. Yes, here we're dealing with a rigid body, so not the particle. So at that time, what you have is like both the kinetic energy for your translation and also kinetic energy for your rotation. All right. So that's what we're talking about. When you deal with a pure rotation, you still have to think about your translation, translation energy, which is your kinetic energy. Um, So here we're writing 1 by 2 as 0.5 in decimal. The same thing, your MV, your G is your reference, the whole square, 0.5 times, and then your moment of inertia, reference point G, and then omega the whole square, yeah? Of course, so we use this equation all the time. Your regular, yeah, I taught it last week for you. So that's your velocity, yes, regular velocity. Your reference point G is equal to your distant regular, yeah, angular velocity omega times, yeah. So r omega is equal to, see like how this the way that they write it is not very accurate. This is not W. I'm like reading this W. This is supposed to be omega. Okay, so which is this one actually? So somebody got this wrong here. Anyway, so when you read it, maybe they don't have a symbol or something. So anyway, so V, yeah, regular velocity equal to R distance, yeah, from the point G on that rigid body, and then you're gonna get your omega times omega, yeah. So kinetic energy body, we're gonna put that right into here, yeah. See, like how we plug this in straight in, and then we're gonna take that 0.5 out, yes, bang. So you're left with this, yeah, and then your mass, and then your Vg is now this R omega, yeah. Since we have a 2 omega, we can take the omega out as well. So we have 0.5, yeah. This we can again combine that together, your moment of inertia and then your mass times your distance, yeah, together as coming from this, yeah, point O instead of G, yes, because there's a moment anyway, so you can combine the two. Don't ask how this come to be, because I have already shown you in the particle, yeah, how we deduce that equation. So right now, just read it like this, and this is the same, and we can add it up, yeah, and we can be able to do it as a moment at the point O. Yes, it's combined between the two things, because we're translating this regular, yeah, velocity into the rotational, which is angular velocity. So we're just writing the equivalent of that in the angular form here. So therefore you can add it up, yes, with your moment of inertia, yeah, which is ing. So anyway, this added up and you will get this, yeah. So don't worry about your equation deductions. I won't ask you. If you get, yeah, this, you can write it two ways: translation part, rotation part, and you can write together from the point O instead of G this way, yeah, and I would be very happy. Okay, and then if you have the rotation, right, happens about the mass center G, then what's the value of Vg? Meanwhile, if we're taking the mass center at G, yeah, we want to know, oh, what is the Vg? So here, the velocity of the mass center is equal to 0 in this case. This is where your velocity is 0, yeah? So when velocity is 0, this part is cancelled out. You're gonna have only that part, okay? When I was talking pure rotation, I jump into this, my brain, right? Because then I still have to, go over that from the beginning. So anyway, so this is, if rotation happen, again, reference point is very important. We're dealing with a G, yeah? At that time, your velocity is 0, yes, because that velocity is at your mass center. At that time, your kinetic energy equation is going to be only that, yeah. Okay, and then let's go into here. Don't worry about the calculus part. Yeah, I'm not going to be asking you any of it. Just listen, yes. So you kind of get the concept part of it when we deal with the work, yeah, of your force. So here, work done by a force. We always have a force times you at least get displacement, which is your change in your position. And sometimes we deal with a little cosine sine. Yeah, I won't be asking you. I will give you straight. Yeah, the 3, 4, 5 triangle thing. So that way you know cosine is yeah. So depends on how the triangle is oriented, yeah. But at least you know your force, and then times your change in displacement. Sometimes we'll have to deal with the cosine sine angle. I will give you the value, and you can be able to get your work done, yeah. So the real calculus basis, we're dealing with a very tiny amount of changes, yeah, in your position or in your angle. Here is your position here too. So at that time, you have to do the integration. But of course, for this course, don't worry about this. We'll just go with the regular one, yeah, which is very inaccurate, but it's still okay. So when the force is constant, your equation, we're gonna do your reduce it, yeah, and you're gonna get something like this. That just showing you the work done. Yeah, the same thing. Work is your force times, yeah, your change in position, which is your displacement. Of course, we're gonna take a look at the force and your angle change, yeah, because your force can never be like always horizontal or vertical. Sometimes it come at an angle, yeah, and this theta, either cosine or sine, depends on orientation. So this theta is going to answer for the angle of that force, yeah, where the force is coming from. So that's going to represent component, yeah, again, of your force acting in the direction of that displacement. Again, every time we break the component down, we have to find something that is parallel to your direction of that motion, okay? So don't forget these fundamental things. So work of a weight. So if you have a weight, you can also have a work done by that weight. So here, as before, your work can be expressed. This is your work. U is for work, yeah. So you're gonna have like a since weight is going down, yeah, usually straight down. So minus and then W and change in your Y axis, okay? So that's when you're dealing with the weight as work. So the force and the movement are in the same direction, going down, yeah. And the work is of course a positive. Here is your x direction, meaning like we're going straight down 90-degree down, yeah. Of course you still have the work because you have a weight on it. So you have the force, which is your weight, times the distance, yeah, which is your delta y. Work is always force time change in change in location or distance or position, and we usually represent with coordinate, yeah, axis. So here in this case, straight down, so y. Sometimes horizontal, so x, yeah. And if your force come in a different angle, we can break that down into components, yeah, we know that already. So if the force and the movement are in the same direction, your work is going to be positive. Again, your force, your motion, if they're in the same direction, work is positive. Opposite, work is negative, yeah. So work of a spring force, again, when you deal with a spring force, usually always, yeah, your spring is attached to a wall, and then of course your body is attached to that spring, and you're gonna stretch it out, yeah, stretch it out and stretch in a stretch position. There are only two positions, and every time you deal with a spring, we always have our spring constant, which is k, yeah. The spring is also taking a distance, so therefore you're dealing with the position. See, as little as here 2, and then final is 2, and then 1 is your initial, yeah. Of course, we're dealing with the spring force. Your work done is going to be minus 0.5, and then your k, and then this, all right. Don't forget the square for this formula. Then we'll get into the forces that don't work. So there are some external forces that don't do work, meaning like work cannot be produced from that type of force. So let's take a look at it. So we have like a reactions, yeah, fixed supports like this. We deal with your IC fixed support, and I show you IC just just take it at the base, yeah, mostly all the time. Don't get into the IC in the body, not yet, okay, just put it at the base. And this is where, yeah, the displacement, so that is where the reaction, which is here in this book, we use N for the symbol for the reaction force. Yeah, here you have your weight right here down, and they usually cancel out. Yeah, so the displacement at that point is actually zero. Yeah, at this little point right there, where your reaction, yeah, forces are acting on this rigid body. So your normal, we call it the normal force. Yeah, normal forces, and then you have friction forces acting on the bodies. And here in this example is this your body is rolling. Yeah, it's not slipping. Yeah, so that's the balance that this body or this motion is doing, and it's of course rolling on a rough surface. They don't work. Okay, so why? Because the instantaneous displacement is there isn't. Okay, zero instantaneous displacement at that point. Again, you might think like, oh, I'm rolling, so I gotta take displacement. Why? Because now we are fixing to a particular point where the normal force strike and your friction force strike. Okay, it's a very weird thing that you gotta train your brain to be able to see that. Yeah, uh, you will get it. Yeah, eventually. The word, the key point is here. Yeah, where is it? Instantaneous, right there. Yeah, instantaneous. We're just considering at that point, a single point. Yes, when your normal force strike. Of course, as this thing rolled, your normal force is striking at the same point, by the way. Yes, you see, not only one time it strike all the time as long as this thing is rolling, but strike at the same point. That's what we're talking about. Yeah, instantaneous point. And we call it, of course, the instant centerizer, IC. So somebody asks, hey, IC, is it only right here? Yes, but the IC, they're infinite IC as long as that thing is rolling. Yes, okay, but it's only hitting right here. Anyway, so this is just one example. Okay, there are many different ICs at different points, by the way. So it depends on the setup of your motion. So don't think too much. Just go step by step. Yeah, be patient. So internal forces do not work because they always act in equal. Again, yeah, and opposite pairs like this, equal and opposite, so they don't work. They cancel out. So the sum of the work is, of course, since the force is zero, yeah, your work, the displacement is zero. There is force, but they cancel out, so the displacement is definitely zero. At that time, your work is zero. Okay, this one is we go into the work of a couple. You know, couple mean like they're paired, kind of, yeah. So the body subjected to this couple experience a general planar right here, general planar dealing with the translation and rotation, yeah. And so the two, you have two forces here, that's why we call it couple, yeah. Do work only when the body undergoes a rotation, yeah. So if you are dealing with a general plane or motion, you have a rotation, right? Rotation part of it for this motion. And when you think about the work, yeah, done by the couple forces, they only work, yeah, when that body is going rotation, going like that. Otherwise, it won't. Yeah. When the rotation is zero, then they won't be, yes, any kind of work because these couple forces is not working. Yeah, they're not working. So if this body is rotating through angular displacement, again angular, yeah, going around, displacement, it's a change in your theta every time you deal with the angle. What our measurement is already taught you, going with angle, yeah, your angle and representation. The symbol is theta. This is just showing you there's a change, meaning like a displacement. You know, your angle is changing from one place to another. So if you want to know the change in angle, we usually write this way, and we call that the displacement. The angle is again is a measurement of the length anyway in rotation. Yeah. So And the work of your couple moments, we write it with a big M right there. I needed you to write the equation here. Got to write it at least one time. It's better you write about 5 or 6 times, yeah, so you kind of get it because we have too many M's, yeah. So anyway, so this is a couple moment. So you have your work, and then that's just a change, a little change, is showing you change from here to there, yeah. So that's your angle displacement, meaning like we have a displacement. So as soon as you have displacement with a force, of course you've got work because your work is the force and the displacement. Yes, okay. Make sure you get that, and then change an angle. Yeah. So if the couple moment again m is constant, then we can be able to take this, theta 2 and then theta 1, which is your final angle and your initial angle, out of it. So this is just trying to write this into here. It's the same thing. Yeah. Your work at m is the same as this with your couple moment down. Alright, so the work is positive if your m and theta 2 minus theta 1 are in the same direction. Okay, reiterating the same thing. Work is positive if you change an angle, which is your displacement, are in the same direction. So here, this is just your work and energy, that we have done it many times. So your initial kinetic is going to produce a final kinetic energy by doing this work. Okay. When you deal with a general plane of motion, this equation is going to state the sum of the kinetic energy, both translation and rotation, because that's a general plane, motion. So you deal with both. Your work done is going to be by all external forces. Your couple moments, equals the kinetic equals the final, kinetic energy, which is again your translation or rotation, because we are dealing with the general plane motion. So you must put it into two different motion, which is translation and rotation in each of your kinetic energy part, initial and final. In each one of them, we have rotation and translation. Okay, try to get it. It's a little bit complicated. I can go fast because I know it. You have to take time. Okay, you have to take time. Don't feel bad if you don't get it right away. You won't. It takes time for you to get this. Okay, we all have to go through it if you want to keep your scholarship. Anyway, so the equation is your scalar equation. Yeah. Scalar meaning like we're not dealing with the direction of each of the quantity inside of your equation. And we will apply that to the system of your rigid bodies, by adding up, summing adding up the contribution from all of the bodies. If you think about more than one rigid body, all you have to just calculate and add them up. Okay, I need to go eat something. I'm so tired. I'll be back, Alright, and we'll get into an example here, We're dealing with a wheel. So you know that's your circumference is your distance, and subjected to force. You have a force, there's an angle right there, and that's a 15 Newton. So we know that we have a distance, radius is 0.4. Gyration, again, radius of gyration of the wheel about its mass center, which is your O, is your center, and since that's a gyration radius, so we write it with a little k, yes, is equal to 0.3 meter. So we want to find the angular velocity, yes, the same thing again and again, angular velocity, dealing with a wheel. So it has rotated 10, revolution. So we already know the revolution, you know the 2 pi, radians. If you want to have change to the radian, and the wheel starts from the rest, gonna start from the rest, velocity, gonna roll without slipping, yes. Okay. So then what you have to do is, in order for us to get to the velocity, you have to plan how in the world to get to that, yes. So first, since this is working, you have force, so and taking a displacement, so therefore you do have work. So we're going to use the work. It is in motion, so we need the energy. Yeah, so we will do the work and energy to solve this problem. Why? Because your distances keep going as the wheel is rolling. Yeah, so that's what we're thinking. Yes, before we do this problem. So we will draw this a free diagram, of course, because we're given with a little animation diagram here. So we're going to transfer that to the force diagram. Then we will calculate by using these external forces. Yeah. Alright, so free body diagram, and here in his example, he just put it right in there. Yes, you can also take it out. Yeah, take out and just draw a circle with the center O, and put all of this information, your force, your angle, and then your radius, yeah, distance from the center to the circumference. And we're gonna break that down at 50. Yeah, so because you have your acceleration due to gravity is down there. Yes, force, and then straight down. Yeah, that's kind of like a weight, and you have your reaction, which is your normal force right there. Your point right here, yeah, usually call it IC loosely. That's where no velocity is if you start to initialize that. Yeah, and of course they cancel out. So your force, of course, yeah, is gonna go into this direction. We break this down into that part and a horizontal part. Okay, vertical and a horizontal part. Vertical part is cancelled out with this, so the motion will go that way, and we'll use the horizontal part of that force. Okay, so that's what we plan out in this diagram to see. And we're just gonna roll without slipping on a horizontal surface. Only the force of that P horizontal component is gonna work for that motion. Yep. So why don't forces PF and N do any work? Because they cancel out each other. Yep. All right. So work, your force, your change in distance. The force is at an angle. Yeah. In this case, it's showing there for you 30. Yeah. So we go cosine 30 because it is a cosine because it's going in a horizontal, component direction. Okay. And then you're gonna plug it in all of that. Yes, of course. In your example, I won't be giving you this uh, integration. Yes, won't be giving you the change. We'll give you a straight. Yeah. So you go in there and then multiply your force 50, angle cosine 30 going in a x direction, which is your horizontal, and then your tan, and then times your pi, and then 0.8, sorry. Yeah, so that's because this one is you have 10 revolution. Okay, so that's how we calculate the distance. Of course, this is a force bar, and this is don't confuse it. I won't be giving you something like this in your exam. Yeah, we'll just go straight with your 2 pi, and we'll use the radians for that. So anyways, this comes from the change. So you would end up, this part is your displacement change in, yeah, positional, this we rolling. So you'll get a 1088 Newton meter for work, force, and displacement. So therefore, Newton for the force, displacement for your m, which is meter. Yeah. Again, we're gonna bring our famous equation, your angular velocity and your regular velocity. All you have to do is just times with r, yeah, and they conserve, by the way. So if you just want your regular velocity, we're just gonna multiply your angular, yeah, velocity with your distance. So your distance here, one radius is going to be 0.4 times your angular velocity, meter per second, of course. Your kinetic energy and position, which is your situation, yeah, before the motion is t1, and that's 0 because your velocity, initial velocity is 0 anyway, yeah, and which is equal to your t2, yeah, with the work with t1. So t2 is your two parts, yeah, you have your translation and then you have your rotation. So your translation is 1 by 2 m, and then regular velocity the whole square, and then your this got to be the whole square up there, yeah. And of course, your rotation part is 1/2, and then moment of inertia, and then your this one is your angular velocity. We have already calculated, okay, this regular velocity, which is 0.4 angular. So we're gonna put that in the whole square. That's gotta be square. Okay, I try to fix it but can't. We can't change their slide, by the way, so we have to use it as they give us, for with their book. So anyway, so this kinetic energy is going to be 6.25 times with this one as your angular, okay, velocity, the whole square. So all you do is multiply this, square this, multiply with that, okay, square this, and then square this, and take that omega square out, okay. The rest of them you calculate it in your Excel sheet or use a calculator and you'll get 6.25. Then we're going to plug that in. So T1 is 0, work is 1088, and then your T2 is 6.25, So we can be able to calculate the angular velocity, which is W squared. So take the square root of it after you after you add this and divide it with 6.25 and take the square root of it, and you will get 13.2 radian per second. We gotta use a radian because you're dealing with the this guy, which is your angular velocity. So rolling with that rate. Okay, then we get into our little concept quiz. So here your rigid body is going to rotate about a center of gravity. So translation of kinetic energy. So we're dealing with the translation energy. It's going to be equal to 0, because it's mentioned the rigid body, it rotates about a center of gravity, so which is straight down, So therefore, at that time, your translation kinetic energy is 0 because the velocity is 0. Translation is your regular velocity. It's just telling you where I show your IC point is, So anyway, but for IC it is connected to the surface. This one is a rotating body, so that's go with your axis, which is you can use as a center of gravity G, so that's a 0. All right, the second one is a rigid bar of your mass M, and then your length you have like L, from here. It's going to release from the rest from the horizontal position. So this is the rest, and you're going to release it, go all the way down, So since it is from the rest, you got the velocity 0. So what's the rod's angular velocity when it has rotated through 90 degrees? So we don't have to calculate it. We just have to find it, here. So you will have to use your angular velocity equation, okay? For you will have to sit down and work. Of course, I am not going to ask you this. So if you calculate it, use your angular velocity, relationship with your length and the mass, and you're going to be getting a 3g divided by L, which is your length, and then square root it, okay? So you're dealing with, this is your center, and that is your length, so kind of like a radius, and it's going down that way, okay? So you have an angle, since this one, let's say like start from 0 and then keep going, okay? So there is a little bit of the calculus in it, so don't worry about this question. I won't be asking you that, Probably I'm gonna ask you this because it's pretty easy to know. This one is a little calculation by using a particular equation, which I have already shown you that you just have to replace that with your M and L here, Alright, we have a 50 kilogram pendulum. We call this a Sharpie, okay, impact machine. You will see it most of the engineering department, okay, for testing. And we're gonna release that from there all the way here. Again, here is your key point from rest. So your angle is going to be 0, So radius of gyration, again 1.75 meter is given to you. We have to find your angular velocity of your pendulum. and it tells you where your angle is going to be is that, so 90 degree, yeah, and which is a little bit similar to this, yeah. Okay, all right, so over there it's just giving you, yeah, the length is that here, see that, of course that's your center here and this is your G point here, yeah. um so let's think about that because it involves a distance going from 0 to 90 degree. We're going to use work energy because it got to work, yeah. It will have kinetic energy for that motion, and in order for this to have that final kinetic energy, it's got to come from the initial resting point with some work, okay. So that is the deal that we are going to work it out in that way. So work done by the external loads. First we're going to draw everything, break it down into x and y. X is your horizontal, y is your vertical. Of course, you always have a weight for this mass, which is going straight down. Mass time your acceleration due to gravity is your weight, okay? You have to calculate the vertical distance, the mass center move. So your delta y, which is this guy, is here, measuring from right there. So that's a 1.25 sine theta, okay? Of course, going down, so therefore negative direction, yeah? Since this is a distance, your unit is a distance length unit, m, okay? Sorry. And then we have to determine the work due to the weight. Because of this weight, this thing is going to move, the chip is going to move from here all the way to 90 degree, yeah? So we're going to use our work equation. Your work is your force and displacement. The change in displacement, you start from here, get to here, so therefore that amount displaced, okay? Weight at that time, your force is weight, its own weight, so W, yeah? So that's your 50 times your acceleration due to gravity, 9.81. And then times your displacement, which is 1.25 times your sine is 90, because it said it so in your angle, yeah? So multiply all of that and you're going to get 613.1 Newton meter. Yeah, that's your work going from position 1 to position 2. Yeah. All right. Kinetic energy part we're going to get in. We'll take our moment, yeah, which is your mass moment, which is this little I right there. So mass moment of inertia, and it's going about this point A, yeah. So you have your mass, you have your K, okay, and that's your radius of gyration given to you in the problem. Multiply that and you will get 153, and this is your equation, okay, in your textbook that you see. So I already showed you that in the previous slides. So you put them all together and you will get that. Starting from the rest position, so kinetic energy is 0, so because of the velocity 0, and your final kinetic energy is your translational and the rotational, yeah, because it's translated and also rotated. So we go back into our translation 1 by 2 mv square, and then your rotation 1 by 2 I, and then omega square, okay? Because this is a 0 out, so you have only the rotation, there's no translation, yeah? So we're going to deal with 0.5. We know I, which is this, put that in, and we will be finding this omega, yeah? Put everything into work energy relationship equation, which is initial kinetic energy, final kinetic energy, yeah? You have to add work in order for you to get the final kinetic energy, which is no motion. We do this amount of work, so the thing that was at rest is now moving, yeah? So that's how you see the equation. So put that in 0, yeah? And this one is 613.1. We already calculated from previous slides. and T2, yeah? So now you're going to get that. So that divided by this, square root it, you will get 2.83 radian per second, yeah? Okay. The next one, you have a link, yeah, linkage right there, and you have a 2 kilogram rods, AB here, AB and CD, yeah, and a 20 kilogram bar, BD, okay? So rod CD is subjected to a couple moment. So every time you have a forces in couple, we're gonna use this, yeah, a big M. So that's a 30 Newton meter moment. Yeah, we call it couple moment for these two forces. And your theta is 0, yeah, and then your rod AB is rotating where the angular velocity is given to you, which is angular velocity omega is 2 radian per second, yeah. So the angular velocity, we will have to find another one, but this time your theta is moved, yeah, to a 45-degree angle. And so it's right there, yeah. A little bit difficult for you to see it because it's kind of like a couple forces, yeah, two things going on at the same time because they're linked, and we call that linkage anyways. It's going that way, yeah. All right, so in order to solve the problems, yeah, we are going to deal with the work and energy because that's what's going on. You work and then you got some kinetic energy in that setup. So first, we do our same thing, mass moment of inertia. Put that into your formula. Yeah, I don't have to say it anymore, and calculate it, and you're gonna get 2 kilogram meter per square. Then we'll get into our kinetic, yeah, and kinetic and regular, yeah, velocity equation. Because the radius is 1, so we just left with the omega, yeah, radian per second. And your final, yeah, kinetic energy, and we have a translation and a rotation. So we're gonna put that in. Yeah, we already know this. So that's for the rotation part, and this is for the translation part. We know the mass, yeah, 20. And then the velocity, yeah, which is this one. And we're gonna take that out all together and solve it. Okay. This velocity is this, yeah. So you can take the omega. So if you can't see it, you can write it down. I am just so used to it. So when I look at it, I saw, right, this is your omega right there, square it. So you can take that out like this, okay? If you can't see it, I would like you to write it down. But I will give you a similar problem, yeah, in your problem solve. And then of course you calculate all of that, and you're gonna get 12, you know, omega square, and then this is your kinetic energy joules, yeah, unit. And then we're going to put that all together, and the omega is a 2, yes. So therefore T1 is equal to 12, yes. T1 is equal to T2. So you end up getting 48 joules, yeah. Of course, don't forget your normal force, okay? All right, here when you break this force down, so that is not it's completely cancel out, yeah. So your work is, there isn't work, yeah, only pure rotations about the axis is happening. So that's why you don't see the work part right there, okay. Okay, after we finish out with our kinetic energy part, we will come into the work part, yeah. So in the previous slide there isn't, yeah, because you have to calculate different, yeah, components right in there. So how we break that down. So now after we break down the work into x and y component, your x is your horizontal and then your y is your vertical, okay. So we'll start doing our delta y, which is your vertical component, going down to minus, yeah, and it's already given to you. This is your 1 minus cosine theta, yeah, that direction. and this is your change in displacement in a vertical direction. So we're going to put that in. Your work is due to this weight of this bar right there, connected to your couple force right there, and change in y direction. So we will put everything right in here. So we have two things going on, this part and that part. Yes, so therefore you have two of them. Okay, of course your delta y, all right, delta y is a 1 cosine. Yes, your theta is 45. It's in your problem. So we're going to put 1 minus cosine 45, 1 minus cosine 45. Of course, just listen. Okay, I'm just showing you how to do it. You might need a paper and pen to write this down, but you will eventually get it. Okay, and this is a 6, and then that's your mass, and then this is your acceleration due to gravity. So this will give you the force. Okay, so that's for this couple. And then you have another weight, a 29.81, and then 1 minus cosine of 45. The same thing, because they're parallel to each other, so angle doesn't change. So if you want work done by the couple moment, so you're gonna write it down, work done, right? M, and then your moment times your angle, 30. Your moment is 30, and your angle is pi by 4, which is your 45, and you will get 7.5 pi. And don't forget this is time, 6, because this is your rod. You have two of them, so that's why we multiply the work done for this 2 with 2. And this is this, all right, bar right there. So that's a 20. Your problem gave it to you. So let me go back and show you. It's right here. So AB is this guy, AB, and then CD. 6 kilogram. 20 is this guy, which is your rod C BD. Okay, this is BD. So let's go back to here. So you get the work done by a couple moments. Again, this problem you don't have to know it. You just listen. Listen to. So you're kind of familiar to how the force is broken down into different. And of course, the force in this example is your weight. Okay. And then we deal with the change in distances like that. So you only need to listen. Okay, I'm gonna just go through one by one like this, so you kind of get familiar to it. Of course, you will do your selected problem for your course. So work energy, we do the same thing, the initial, and then your final. You do some work to get that motion to this, initial kinetic energy. Initial kinetic energy is 48, and we did this amount of work, okay? And we add them up and take it out, and that's equal to your final kinetic energy, which is 12 angular velocity the whole square. And from here, as you solve it, you will get 3.49 radian per second. That thing is going. Okay, all right. Just a little quick, just listen. Okay, so here you have a disc and a sphere. You have each, all right, mass m, you have radius r. You are release it again from the rest, the same thing again and again. So, and it goes 2 full turns, turns, and your which body has a larger angular velocity, So you have to find which one has a larger velocity, angular velocity. So omega. Of course, you assume the road is without the slip. So if you have to sphere, given to you here, a disc and then the sphere. So what you have to find is, the body with the smaller, smaller mass is going to gonna create a faster velocity, yeah, because you don't have to carry that mass a lot. Um, where the kinetic energy has a mass and a velocity, right? So if you want to know which body has a larger angular velocity, that's the one with a smaller, okay, the one with a smaller uh, MMI, yeah, which is a mass moment of inertia. So when you think about the shape of that, this always have like a bigger, yeah, mass moment of inertia than the sphere, yeah. Why? Because of the shape, yeah. This is a disc, and then a sphere is kind of like a little circle, okay, a little spherical ball, okay. So because of the shape, then we can be able to choose the sphere, yeah, with the smaller mass moment of inertia. So in this case, it's a sphere, yeah. So right now you wouldn't understand. Okay, just try to get it like, yeah, try to get it like if they have the same mass and radius, yeah, and but they have a different shape. Always sphere has a lower, yeah, MMI, mass moment of inertia, meaning like it will move, yeah, faster. So therefore, angular velocity will go larger, yeah. C and D is out right away because you can determine the angular velocity and um, the sphere and disk, they're not equal, yeah. Therefore, C and D is out right away, and you have to choose between the sphere and disk, but they have the same mass and then the same radius, yeah. Only the shape is different because this disk, yeah, this is a disk, and that's your radius. The shape of the disk, all right, it's not the same as your sphere, yeah. In this case, the sphere is gonna go with a larger angular velocity. When you have a slender bar again, M length L, you're gonna release it from the rest, okay. Now this time we want to know the work done. So the work done is again your force, yeah, and then change in displacement. So it's this, yeah. You have M and G as your force, which is your weight, and then L, right, divided by 2 is half of that L is going to be rotated through 90-degree, yeah. So 0 and then go all the way here. So it will go about half of that L is going to be your displacement, okay, and times that, and that is your work done. And it is 1 by 2 is because 90-degree, yeah, going down. Okay, planar kinetics of a rigid body. We will get into conservation of energy. So how we deal with that, let's take a look at it. These are just the objective, yeah, and planning, and this is just reading your quiz from your textbook reading. So elastic potential energy. So after you have read it, you can point it out as this, yeah. So 1 by 2. K is elastic, so it's kind of like your spring, right? And then of course opposition, yeah, the whole square. The kinetic energy of a rigid body consists of kinetic energy due to well, since we're dealing with a rigid body, we have to think about translation and also rotation, yeah. All right, application. Here is a torsion spring at the top of your garage door. Wind up, yeah, as the door is lower. So as you go down, it's going to wind up. And when the door is raised, yeah, move up, the potential energy is going to be stored in that spring right there. And translated that into gravitational potential energy because you will keep at that height, yeah. So first, kinetic energy, motion, and then when it go up, it's going to stop right there, gaining a height. So you have your potential energy. And that potential energy is your door's weight. So thereby making the door, right, really easy to open. Why? Because you're changing the kinetic energy and the potential energy to keep that door right up there. Of course, you can draw, like this diagram there and giving points, C and A and B, and then you have your 3 meter, and then you have your 4 meter for these dimensions right there. So when you do the application, we always think about the torsion, the spring stiffness is important when you deal with your rotation, angle. So these are the things that we think about, in this application. All right, the next application is you have your 2 torsion springs, we will use that to open and close the hood, of your car. In this case, is your pickup. So we're going to assume the springs are uncoiled when your hood is open. And we can get the stiffness of that, spring. Here we have 2, so each one of them. So that your hood can be lifted, easily. There's no external force applied to the hood when a person is opening that one, So gravitational potential energy of the hood, right? And then your torsion of that spring stiffness, you have to think about whether they are related to each other or not. Okay. So anyway, this is just showing you the energy, transfer between them. So that's how the conservation, of energy is happening. Like I say, the energy is conserved every time there is like a domino, touch effect. So one body to the other one. So motion can be transferred to the next body through your energy conservation. So conservation of energy, simpler your energy, we call it energy method where your energy is conserved. So you have your working energy, your equation, remember that. And we always use that to solve the problem. So the problem parameter, your key point is your distance, so distance is a parameter every time you deal with your work energy relationship. So when conservation of energy is a good approach to solve the problem. So if that's appropriate, then we usually use conservation of energy, to solve the also you can use a principle of working energy. So it depends on the problem. You use one of them, or both of them sometimes. Of course, your work conservational work is easier, for you to use, because work energy has like a 3 situation too. Your T1 and then work and then your T2. But if you use a conservational force, right? Work of the conservational force, and then your force is conservative. Well, anyways, right now you won't get it, so we will get into it little by little, so you can see. So the very first one is conservational force. So the force is conservative if the work done by the force is independent of the path. So every time you have a force, there is a path. So work is usually done if you have a force, and then of course if you have a change in displacement, which is your path. So when that force is independent of that path, then your force is conserved. Right now you can't see it. You have to see with a diagram. Okay. So the work depends on the initial, again, finite position of your object, because that is defining the change in your position, which is your displacement. So with the path, of course. So between the position of no consequence, of course, and then you have to use a force. So conservation forces you have gravitational forces, and then you have elastic forces. They're all conservative, yeah, forces. Your weight conservative, your spring conservative force. If you think about the force that isn't, yeah, conservative, so all other force except the gravitational forces and your elastic force, of course, your spring stuff. All right, and then we go in a rigid body is acted upon, yeah, by a system of conservative forces. So the work done by these forces is conserved. So meaning like if you have a rigid body and you have all of your conservative forces acting on it, then the work done by that force is also conserved. Yeah. So the sum of the kinetic energy, your potential energy, is going to be the same. Yeah. And we call this conservation of energy. So your kinetic energy plus, and then your potential energy, you know, T is for kinetic, V is for potential, is equal to kinetic energy plus your potential energy for condition 2. Yeah, well, this is Planar and that's our initial, by the way. And it's always going to be constant. So in other words, your rigid body is going to move from one position to another when acted upon by only conservative forces. Kinetic energy is converted, you know, to potential energy, and then vice versa, meaning like going back and forth between the kinetic energy and the potential energy. Okay. So anyway, so this is your equation for conservation of energy. So the gravitational potential energy of an object, yeah, is again we're coming into the function. So function of the height of your body's center of gravity above or below a datum. So you have, this is just datum and just a reference point, you know, that you're measuring your vertical, right, distance in this case to the point center point G. So this is the center of gravity, so therefore we use the little, yeah, G point, call it, of course, your weight, yeah, and here is your potential energy. Potential energy, you always need the mass, right, times mgh, yeah, so mg is your weight and the h here is your height, which is your yg. Going down, yes, you also have a negative, yeah, vertical distance to g from your datum. If you go down from the datum point, then you get the minus. Yeah, that's just where you're measuring. As you measure below, then go minus. If you measure above, then go plus. Yeah, it's kind of like your Earth, and then you're measuring a rocket at a height, and then you can be able to find, yeah, the instantaneous uh, potential energy of that rocket. If you think about the satellite, the same thing, the Earth, and the vertical distance is going to be the height of that satellite. Yes, and then the weight is the satellite weight is going to be your force. Yeah, so like that. Of course, if you go down into the Earth, then there is, yeah, minus the vertical distance. So that's what we're talking about, the datum, the measure point. So gravitational potential energy of a body is found by the equation, yeah, and we have this one is your gravitational potential energy, and that is equal to this one is your vertical, yeah, distance, and then this one is your weight. Okay, so gravitational potential energy is positive. So if your yg is positive, because the weight has, yeah, ability to do the positive work, and when the body is moved back, yeah, to the datum, meaning like, oh, right here is your datum reference point. All right, elastic potential energy. So spring forces are also conservative forces. So the potential energy of the spring force, we're dealing with, yeah, Ks for the spring force, and it's found by this equation we always use. So potential energy is equal to 1 by 2 for the spring constant is there, and then the opposition square, yeah, which is this. All right. So elastic potential energy, it's always positive, yeah, because it stretch out like that. Your unstretched position, yeah, is going to be always 0, yes. When you stretch it, then you take a distance, which can be restored back when you release it and go back to the unstretched position. Procedure of analysis, not just for reading, but it's always the same. So if you have like a velocity displacement conservative force systems, yeah, we're going to start with the potential energy, find it and use this equation. Kinetic energy, use that equation, and then of course you apply the energy of conservation of energy equation, yeah. Kinetic energy again 1/2, angular, yeah, rotational kinetic like this, translational kinetic with a regular v, yeah, here rotational with the angular velocity omega. Air potential energy, again you have your g, yeah, and then your e is just showing you the initial position and the final position, okay. And each one of them you can find this way. This is your weight and then change in, yeah, distance, and this is your spring is 1/2 constant k, and then s squared. So here it's just showing you the total, yeah, total potential. I forgot to tell you that. That's just your potential energy, yeah, due to gravity, the potential energy due to the elastic. E for elastic and G for gravitation. Alright, the next example, you have a rod AB that is 30 kilogram weight. Your spring is attached right here, yeah, and it is making a 45-degree angle, and the spring constant is K, and that is 300 Newton meter, and we want angular velocity. Your rod is AB, yeah, your theta is 0. That's your first position that you need to find this angular velocity at, starting from the 45-degree angle going backwards, yeah. So if the rod is released from the rest, yeah, when this is a little bit tricky because your rod, yeah, is rest, yeah, but the angle of rest is at a 0, theta is a 45-degree, okay, and you're gonna go to theta 0, yeah. So that's what it's saying. So we're going to use the energy conservation equation, the same thing for all conservative forces, and your distance, yeah, is your parameter. Here your distance is in terms of theta, and then the potential energy and the kinetic energy of the rod. Okay, you're going to just put it like state 1 and 2 for initial and final. Alright, so potential energy, we're going to use our elastic potential because you're dealing with a spring constant here, yeah. So we're going to start finding our VE. So your VE is 1/2 ks squared, yeah. You can put that into there, yeah. You'll have 300 and then a 1.5 minus 1.5 cos 45, yeah. For this, so 1.5 is here, cos 45 is here, times that is your component, yeah. When you take that out, you're going to get the final and initial, yeah, your S1 and S2. This is where showing you the displacement, and then the whole square. Gravitational is your Vg. Vg is equal to your weight and then your vertical distance. So M, you have this, your rod is given, yeah, 30, yeah, and then your G is 9.81, yeah, meter per second square, and then your Y is going to be this, yeah, 1.5, and then sine, since it's a Y axis, your component is sine 45, and so that's what you get, yeah, all of that. And this half is we're going back, yeah, to from 45 to 0. And this half, of course, is you're taking it, yeah, half of this potential energy, yeah, because it's a gravitation, so your G point is half, yeah. And then of course we're gonna get your total is at this and that. So when you add it, you're gonna get this. After we finish dealing with the potential, we'll get into kinetic. Kinetic initial is 0. Kinetic final, yeah, we will put in 2 parts. Again, the same thing. as we always do, yeah, your regular velocity, and this is your angular velocity part. Okay, so we're gonna plug it in, all of it all together, yeah, mv squared, and then this is your mass or moment of inertia, and then of course you put everything that you need to put for this rod, yeah. And don't forget, we're going at the center of mass, right? So your kinetic energy for each part, rotation, and that's your translation, and you add them up. Then we're gonna use our conservation of energy. So we write down our final, yeah, put them all together, calculate it, and you're gonna get this angular, yeah, velocity. Angular velocity, we're gonna link it back to your regular velocity, yeah, distance time your angular velocity, and you put r as 0.75. So you're gonna get and put it into here, yeah. 2 is just telling you the state 2, which is your final position. Then we will use our conservation of energy. Your T1V1 is equal to T2V2, and we're gonna put all the information that we know into there. Yeah, your T2 is right here. Of course, they're 0 because they start from the rest. And you solve it. We already calculate V2, yes, in the previous slide. And when you solve it, you're going to get the omega square, yeah, is 3.36. If you take the square root of it, you're going to get a different one, yeah. And so you get, so after square root, you get 3.36. Sorry, this is not square root. I forgot. Yeah, he is using the same. This is supposed to be subscript. Yeah, so that's a W at the state 2. So final W is 3.36. It's already done for the square root. Sorry about that. So this is writing. What I'm saying is a W squared. Yeah. So in this case, they're using the state 2 as a W, not W omega 2. Yeah. So this is supposed to be the subscript. So already square rooted, so that's a 3.36 radian per second. We go into another example, 30 kilogram rod. It's going to be at rest, and your theta is 0. Your spring, is and stretch at that time when your theta is 0. And we want to find the same thing, angular velocity of the rod, when your theta is 30 degree. So since the distance is again per meter, and all forces doing work are conservative because they're gravitational, and also spring. So we'll get into potential and then kinetic, and then we're going to use a conservation of energy. So that's the deal. So potential energy, we start to find the same thing. Yeah, your G, give it a state 2, put the same equation right in there, calculate that. We'll get the V, which is your potential energy for your spring, calculate it, use a spring equation, constant K, and S squared. And of course, you add them up together, 2 of them, and you will get the total V. Then we do the same thing for the kinetic energy. First, we try to find the T at rest, 0, and T2, we have a translation and the rotation part. Plug them in, and you will get it. And of course, we're looking for the angular velocity, so you always have angular velocity, omega the whole square is right in there for state 2, final mean 2 here in this example. Then we will use conservation of energy, which is potential plus kinetic, and then potential plus kinetic. They don't change, they're the same. So the initial all 0 because they're starting from rest, and then your final position, kinetic energy, you have this with your omega in it, and then your potential energy is this, your spring, and then your gravitational, potential energy. And from here, you solve this equation, and you will get your omega, which is your angular velocity, 3.04 radian per second. Now we'll get into the concept quiz. And here, so at the instant in this diagram, yeah, your datum is here. So when you carefully look at it, we're dealing with the spring. So you already know, yeah, half. And then K, of course, so S squared. So if you use the equation, what this one want you to find is the potential energy. So you have to deal with the your regular, okay, regular and a regular gravitational, and the other one is your spring, yeah. So which is this guy. So if you want to change, so you have to minus it out. Yeah, first you go potential energy initial, and then the final, and then you minus that. Yeah, and you will get, which is this one. The rest of them are kind of not right. This one you can just get rid of it because you don't even have the change. Change always is between the final and initial, so you can get rid of A and D right away. Yeah, so you're left with B and C. So when you take a look at it, B has a minus. Yeah, so all the potential energy change is positive. So that's how I chose. Pretty easy, yes. Even if you don't know how to plug it in, yeah. If you don't remember it, you know that, oh, I'm doing a change, so I gotta take it out, yeah, minus. So here, so you get rid of this and this. Oh, yeah, the change is always positive, can't be negative. So this one is a double negative. So if you take it out, you would end up with a negative value, which is against the change rule, yeah. So it's this. See, like it's same as your SAT, by the way, yeah. SAT, how to choose it. So that's how we choose. Alright, the next one is determine your kinetic energy of that risk. Sorry, this is different. So determine the kinetic energy of the disk, okay, at that instant. So since we have to find the kinetic energy, we're gonna take a look at it. Yeah, they are kinetic energy. Yes, both of them are, because you see the half, see the mass, and then your, of course, this is your 3 meter per second is your V, yes. So you have both of them, and this is your I, and then your, of course, so they're giving you the translation and the rotation, yeah. So therefore we'll have to a translation and the rotation, because of the spring, yes, is attached to it, so we use this one, okay. So A and B together, yeah. D is wrong because we do have the kinetic energy, so that this D will come out right away, and you carefully look at A, B, and C. That's the kinetic energy, that's the kinetic energy. Dealing with the instant, your setup has two things going on. One is a regular translation, yeah, and also the rotation. So we chose both of them for the kinetic energy. Okay, so answer is C. All right, the next one is you have a cylinder, yeah, a 6 kilogram bar AB, horizontal at rest. Your spring is here and stretched, and your length is 1.5 meter, and the spring constant is 12 kilogram newton per meter, and we want to get the angular velocity of the bar, yeah, when it has rotated clockwise 45 degrees after being released. And we have to determine the potential energy and kinetic energy for both positions. So potential energy, we do the same thing for the spring. Yeah, your length is 2, so we'll have to find. So because at position 1, your gravitational potential energy is 0. Yeah, because there is no height. Yes, at position 1, which is this, and the elastic potential is going to be 0 because it's an end stretch. Yeah, so V1 potential energy for the position 1 is 0. Then we're going to use a geometry to find the spring length, all right, at position 2, meaning like final state, okay. So that's how we find the spring length. So L. Of course, don't worry about it. I won't ask you. Yeah. So just listen to this problem, how we work that out. And this is where we get your L, elastic potential. Yeah. That's your VE. And that is 1 by 2, and then K, yeah, S squared. And we put that in, and you will get your potential energy for elastic, the spring part. And then your gravitational energy, of course, you're going to weight, yeah? Use the weight of that rod given to you here as 6, I think, kilogram, and the acceleration due to gravity, yes? And then multiply that with your vertical distance, yeah? So if you listen to about that, you should get a potential energy. Oh, hey, I have a weight component, and then I have a vertical distance. And she is always using, yeah, the mass and then time of the gravitational, yeah, acceleration due to gravitation will give me the weight, yeah, and then times the vertical distance, yeah, from a data reference is going to give me my potential energy, yeah, gravitational potential energy. So after you calculate both of them, we will get into, of course, kinetic energy, yeah, position 1, 0, because your theta is 0, position 2, 45. We're going to put that in, yeah, mass moment, and then this is your angular velocity, omega squared, yeah, so we get it. And then use your conservation energy equation again, yeah. So lecture, just listen, yeah, I'm just going to run through and you kind of get it. Don't really get it, but you will get it, okay, just listen to it. And then your, of course, your kinetic energy, and then potential energy, position 1, kinetic energy, potential energy, position 2, okay? I'll put them all together. And since angular velocity is what we want to look for and we don't know, you can solve that, yeah, equation out, calculate it, and you will get 2167, yeah, radian per second. So we're doing the same thing again and again, yeah. Another one, 250-pound block released from the rest. Your spring is unstretched, yeah, the same thing. It's just the setup is animation is different. And then your drum weight is 50, yeah, so you're dealing with again your gravitation, yeah, because the weight is there, and of course your spring, so therefore you have your spring constants here, so 0.5 feet, yeah, about the center of your mass is right here. So we want to find the velocity of the block after it has descended, okay, 5 feet, so this guy. So we need to do the conservation of energy, okay, from here to here and here to here. All right, first we're going to determine the potential energy, yeah. So we do the same thing, potential energy, position 1, 0, position 2, yes. The spring is going to be stretching, so we'll put in there, yeah. And you will get that. Your spring elongation, when it's pulled out, is going to be 2.5, yeah, feet. So just listen, yeah, you don't really need to, I won't ask you this one, yeah. Your gravitational potential energy will be using your weight and your vertical distance, and we get that. So it's going down, it's minus, yeah. Your elastic potential energy will use your spring, yeah, so Ks squared, and we're going to put what we've got, K is given here, and your S squared, and we just calculated it, okay, because it's given to you. And we get this 234.4 British, yeah, or English system is feet pound. Then we'll get into kinetic energy, the same thing, 0 for the first state, second state or second position, you're gonna have your m, yeah, v squared. And then the other part, which is your rotation part, which is 1 by 2, and then mass moment, yeah, mass moment inertia, and angular velocity, the whole square. We put them all together, yeah, and you will get your IO, and put that back into here, and you will get your T2, yeah. Of course, we don't know the regular velocity this time, we're given the angular velocity this time. Of course, your V2 is 0.75, yeah, angular velocity. So this is where you replace your you replace your omega, yeah, omega the whole square, and put your v. So that way we can be able to calculate the regular velocity. So anyways, then we use our conservation of energy, yeah, equation, put them all together, all the things that we know. The only unknown is your regular velocity, yeah, which is a 15.5 feet per second after you solve this. And direction, of course, because that's a vector, so it's going to go straight down. All right, the last one is your quiz. And this quiz is asking you about the block. You know, we have A and B released from the rest, so that's 0. And your disk is going to turn 2, revolution. And then your V2 of the system is going to include a term. So that's V2 mean the final, V is your potential, energy of the system is going to include. So only the 40, only the 80, only the 2 blocks, you're dealing with the 2 blocks, and they are connected to each other. So the potential energy for the state 2 got to include both of them, so therefore C. D is just a disk and then both blocks. This is just creating the motion, it's not in it. So therefore we're gonna take care of only the 2 blocks, because we're dealing with the potential energy of the system, where the movement, is changed. So here, so this is where your kinetic and potential energies are transferring, back and forth. This one is just a medium, it's just carrying this 2 weight on this disc, so we doesn't really move, it's just providing the angular velocity right in there for this 2, so therefore when you deal with the potential energy, we're just measuring the vertical distance for these blocks, not that, so therefore we're going to choose C. Then a slanted bar, again your mass and then your length, gonna be rest and just let it go down again, and you're gonna have your kinetic energy, which is your T2, and it's asking you, okay, what's the kinetic energy of the bar when it has rotated, so how is it going to rotate? So everything that's got to deal with the rotation, got to include the angular, velocity. So this is all gone, so only B and D. Why? Because I'm seeing the angular velocity right here. Now your bar, yes, has gone through 2 types of motion, not only pure rotation. So there's another part which is your regular, so that's regular kinetic energy is there in this total kinetic energy. So therefore it's D straight up, You don't even have to remember any of the formula. Just by looking at it, you understand. Oh, I'm dealing with the rotation, so omega. Oh, wait a minute, I have regular velocity and angular velocity, so I am dealing with the translation, the rotation, kinetic energy, yes, for this system. So choose D right there. This is how we solve the quiz. Some students go into too much. If you go into too much, you can't see. You gotta put yourself a little bit back out and you take a look at it, so you can be able to solve these things right away, without even remembering the equations and things like that. So if you're trying to remember the equation, that's too smart. If you want to work smart, then you have to know how to see what you're looking at. Don't get into confusion. I don't like when my students telling me I'm confused. So if a student is telling me you're confused, I'm thinking this student is not intelligent, because he can't see the differences through it. Whether that person explain it in a right way or not, you should have intelligence to go through that confusion and solve it out, independently without anybody else's help. So that is called a true and pure intelligence. It's in your head. You have a brain, so use it. There's nothing to be confused about. People who are confused are those who don't have the brain. Okay, so make sure don't use I'm confused for fun. It isn't fun, because there are people who listen to you will think you don't have a brain if you're confused because you're not using it. And other people can definitely confuse you because you can see through it. Yeah. So intelligent people, they never confuse, even if they're talking to somebody uh, who is explaining in a wrong way, they can see through it. Okay. So try to study to attain that type of level of intelligence. Yeah. That should be your goal. Okay. So at that time, all your confusion will fall out. Okay. Well, that's it for the chapter 18.